All right, last functional group. We have esters. So esters are going to have this structure going on here, okay? So they are going to have this C right here, the double bond O to an O. So it looks really similar to what we saw with our carboxylic acids. The difference, though, is this guy over here, right? When we had carboxylic acids, that was just an H. But now it's not an H. Now it's a CH3. So anytime that you find that you have some C's over here, right, or you'll notice down here, I've written that formula with an R and an R prime. Okay, so R and R prime, I know some of you are in calculus, so like, oh no, the prime. It just means that the R is different than the R prime. Basically, these can be anything. So it could be a hydrogen, it could be 2 carbons, 3 carbons, 4 carbons. We don't actually know what they are, but they're something. But whenever we see that we have some carbons over here, that's COO, and some more carbons over here, that's kind of how you know that you are looking at an ester, okay? So if you want to name an ester, ester naming is a little bit confusing. The reason it's a little bit confusing is we haven't done types of reactions yet, but that is where we are eventually going to, is you'll notice, here's my ester, right? So how an ester is formed is that a carboxylic acid, which is what this is over here, combines with an alcohol, okay? So we have a carboxylic acid plus an alcohol. So over here, when we go to name this, we always need to find the C double bond O to the O. This is where our molecules joined, okay? So find the C double bond O, find the O. It could be on this side, it could be on this side, but wherever that O is on the other side of the C double bond O, just kind of draw a line through that, and that's going to represent your split. So whichever has the C double bond O, which in this case is everything to the left of the line, that means that was my carboxylic acid. And this over here was my alcohol. Okay, so that C double bond O is how I decide that this part was the carboxylic acid and this part over here is the alcohol. Okay, so I need to know that because they're going to go into different parts of the name. Okay, the root is going to be what was originally the carboxylic acid. So originally had that C double bond O group, okay? And that's going to go in your root, okay? And it's going to determine the name of your parent acid. You need to identify the suffix. So when it comes to esters, right? If you think about a carboxylic acid, which is what part of it is, it ends with anoic acid. We're going to get rid of that oic acid part and we're going to replace it with O8, okay? So we're going to figure out what was the carboxylic acid, how many carbons are in it, and then we're going to change the ending from anoic acid over to ANO8 because esters end with O8. So your prefix, normally the prefix tells you the size and location of any side chains. When you are dealing with esters, it doesn't. When you're dealing with esters, that prefix is giving you the name of that alcohol, right? And that's why I showed you a minute ago how you can divide that ester into the carboxylic acid part and the alcohol part, because you need to be able to know what the two parts are so that you can name them. So whatever the alcohol was, it's going to go into the prefix. But you are going to change the ending of it to YL, because that's generally what we do with things that go into the prefix, right? We think methyl, propyl, benzyl, that type of thing, okay? So here we have an example. So let's look at how we're going to do this. So first, I want to recognize that this is an ester. And I'm going to recognize that it's an ester because I have this double bond O, and then I have a carbon chain over here, okay? So step one identifies an ester. Once I know it's an ester, I then need to know that I have to figure out where was the alcohol and where was the carboxylic acid. So you find that C double bond O, which is here, and then, oh, the O isn't over here, it's over here. So that means they joined over here, right? Where this over here must have been my carboxylic acid, and I know that because it has the double bond O. And this over here, by default, then must be my alcohol. So we said that whatever was the alcohol is going to go into the prefix, right? So it has one carbon here, and a second carbon here. So when we have 2 carbons, we use the name ethyl. Okay, we then have a space. So the alcohol goes in the prefix, we change the ending to YL, then we do a space. Then what we're going to do is we are going to put the name of the carboxylic acid in the next part. So where are the carbons in here? Well, here's 1, here's 2, here's 3, and here is number 4. Okay, so because we have 4 of them, we're going to use the name prop. So prop, and, right? Because normally this would be propanoic acid, but we said we would change the ending from oic to O8. So this is ethyl propanoate. So one of the biggest challenges when you are naming organic compounds or drawing organic compounds is that you kind of have to follow a couple of steps, right? And if you think about these lessons, they've all kind of been broken up into individual functional groups or individual families. And then all of a sudden, everything's getting jumbled together, right? So the first thing you always want to do is decide what set of naming rules should you be using. So what family does something belong to? So that's definitely always the first thing you want to do, is figure out, what do I have, right? Do I just have an alkane? Do I have an alkene? Do I have an ester? Do I have a carboxylic acid? So I'll pop up on D2L. I've got this sheet. It's kind of like a big sheet. It might be awkward to print, but you could probably just use it to like maybe make some little like study notes or flashcards or cue cards, which are definitely helpful in organic, because as you're seeing, this is all memorization, right? Organic is that one unit. If you have any parent or any sibling who has taken chemistry in university, usually organic is the one that everyone just kind of goes, ugh, organic. And that's because it's all memorization. There's no logic, there's no math, there's no like, oh, I can get my calculator out and it can help me. Like, there's none of that. It's just a whole lot of memorization of different pieces. So step 1 is always to figure out, what family does this belong to? And then based off of that, what do I actually do, right? So things you kind of want to make sure that you can recognize, I guess, would be from looking at a picture, what am I looking for to know if it's an alkane or an alkene or an ester or an alcohol, right? Or if I'm given a name, what is it in the name that tells me what it belongs to, right? So here, okay, I've got 2 parts of a name and it ends with anoate. Well, I want to make sure that I know that anoate means something as an ester. Or I see that it ended with anol. Okay, great. I know it ended with all, it must be an alcohol. Or it ended with ine, so it must be an alkyne. Okay, so kind of make sure that you have those pieces down, because it's going to make your life a lot easier with organic. So some properties of esters, right? So these are somewhat similar to the alcohols and the carboxylic acids that we've been dealing with. The difference, though, is these don't have an OH, right? They have a C double bond O and then a C to an O to another C, but there's no OH. So what that means is they have an LDF, right? Because all of these molecules have LDF, and they have a dipole-dipole because they have oxygen and they're polar. But they do not have a hydrogen bond, okay? So when we think about where that's going to rank them, we said that alcohols, carboxylic esters, carboxylic acids had all 3 intermolecular forces. Esters have only 2. So they're going to be above alkanes, enes, and ines because those only had LDF, but they're not going to be above the others. Pattern-wise, these are going to follow that same check mark pattern that we saw before. Okay, so if we go back to our little pattern that we had going on here, I'm going to try to pick a color I haven't picked yet. Okay, so we had red as alkanes, blue as alkenes, this green as alkynes. We then said purple was our alcohols, and the gray was our carboxylic acid. So now when we add esters in, they are going to follow the same check mark, but they're going to be lower. The reason they're going to be lower, they don't have that hydrogen bond that the other ones had, okay? So that's kind of your final diagram of what all those different melting point, boiling point trends look like. So sometimes they're going to ask you to compare within what they call a homologous series. So a homologous series would mean that we keep everything the same except we add an additional carbon to the chain, right? So if you think of methane, ethane, propane, and butane, they all belong to the same homologous series because everything about them is the same. We're just adding an additional carbon to it, right? Same deal if I were to compare methanoic acid to ethanoic acid to propanoic to butanoic acid, right? They all belong to the same homologous series. So for the most part, within a homologous series, we're generally going to find the more carbons we have, the higher the melting point and the higher the boiling point is going to be, simply because of LDFs. The other comparison they're going to ask you for is going to be to compare things that have the same number of carbons, but that belong to different organic groups, right? So they might ask you to compare a carboxylic acid to an ester, to an alcohol, to an alkane, where they all have 4 carbons. So definitely kind of this little graph that we have going on here is a piece that you do want to make sure that you have down as well, okay? And again, that other kind of physical property piece that we have talked about has been our solubility, where that really doesn't change too much, right? We're still looking at things that are aliphatic are going to dissolve in hexane. Things that are aromatic are going to dissolve in benzene. And things that are polar, which would be our esters, our carboxylic acids, and our alcohols, are going to dissolve in water when they're small, but when they're big, they obviously are not going to be soluble in water anymore, okay?